Hi, welcome back to educator.com. Today we're going to talk about the properties of quadratic functions. In the previous lesson we worked on finding the roots of quadratics. To that end we learned how to complete the square and we derived the quadratic formula which tells us the roots of any quadratic polynomial. In this lesson we'll continue working with quadratic polynomials. We'll explore another important feature of quadratics, the vertex, along with its connection to the shape of the graph. In addition, we'll also see a new alternative form to write quadratics in that will give us a lot more information than that general form ax squared plus bx plus c that we've been used to using so far. Let's go! Let's take a look at the shape of a quadratic function's graph. We call this shape a parabola. So the parabola has this nice curved shape on either side, and we're used to making these. We've been making them since probably pretty much right after we learned how to graph in algebra. We've been learning how to make parabolas, parabolic shapes. So we're pretty used to this, and you see it a lot in nature. If you throw a ball up in the air, it makes a parabolic arc. In fact, that's where the roots of the word parabola come from. They have to do with throwing back either in Latin or Greek. I'm not quite sure. Anyway, if we see this kind of shape in every single quadratic function that we graph, we get this parabolic shape, a parabola. No matter the specific quadratic, this shape is always there in some form. It may have been moved, it may have been stretched, it might have been flipped, but it's still a parabola. It's still got this cup shape that's symmetric. The graph of any quadratic will give us this symmetric cup-shaped figure. As we just mentioned, a parabola is symmetric. The two sides of a parabola are always mirror images. If we look at the left side and we look at the right side, they're doing the same thing all the way to this bottom part, right? And if we go up, we keep seeing the same thing. We don't have arrows continuing it up, but it's going to be true forever. As long as we're going up, it's also going to be true on this thing. Formally, we can draw a line called the axis of symmetry that the parabola is symmetric around. So if we go to the right at some height, and we go to the left at some height, at the same height, we'll notice that the distance here is equal to the distance here. If we do that at a different height, like say here, these two are going to be equal as well. So that's what we've got for symmetry. There's this axis that we can draw down the middle, this imaginary line that we can put down the middle that is going to make it so that each side is exactly the same as the other, that each side is a mirrored reflection, that they're symmetric around that axis of symmetry. We call the point where the axis of symmetry crosses the graph the vertex. So where that imaginary line intersects our parabola, we call that the vertex. Informally, we can think of this as the point where the parabola turns, right? So it's going down, it's going down, it's going down, and then at some point it changes back and it starts to go up. That point of changing where it switches the direction it's going, whether up or down, or if it's coming from the bottom, going up to going down. That is the place of turning. It's changing its direction, and we call that the vertex. So formally, it's the midpoint for the symmetry breakdown, but we can also think of it as where it changes directions, the turning, sort of a corner as much as a nice smooth curve can have a corner. Just as the graph of every quadratic has a parabola, we can now see that every quadratic has an axis of symmetry and a vertex. So if we go back through all of our previous ones, our original function, f of x, that has a vertex down here, and then it's got an axis of symmetry through the middle. Our g of x right here, that one has its vertex down at the bottom and an axis of symmetry as well. Our h of x in green, it's got its vertex right there, and while it's not quite even on the halves because just the nature of the graphing window we're looking at, it still has that same axis of symmetry. If we could see what happened farther out to the left, we would see that it is indeed symmetric. And finally, I don't actually have the color yellow, I don't have the color purple, so I will use yellow awkwardly for this purple color right here. It too has the same vertex and it's got this axis of symmetry. So whenever we draw a parabola, we're going to have this vertex and we're going to have this axis of symmetry. Now, how can we find where they're located? Where does this vertex occur? Where does this axis of symmetry occur? We know where the vertex and axis of symmetry are for the fundamental parabola, our normal square function x squared. That one's going to be easy. The vertex is at 0, 0, we just saw that, and the axis of symmetry will be a vertical line x equals 0. Real quick tangent, why is it called x equals 0? Why does that give us a vertical line? Well, remember, one way to think of a graph is all of the solutions that are possible, all the things that would be true. Well, if we've got x equals 0 here, all that means is every point on this graph where the x component is 0. So that's going to be everything on this vertical thing. So we're going to have everything on the vertical axis will wind up being x equals 0, right? It might have, we might have 0, -5, or 0, 5, or 0, 1, or 0, 0, but they all wind up being the case that x equals 0 for each one of these. So that's why we wind up seeing a vertical line is defined as x equals something, because we're fixing the x, but we're letting the y component, the vertical component, have free reign. All right, now, end of tangent. What about those other different parabolas, the ones that aren't our normal square function that we're used to, where it's pretty easy to figure out where it's going to be? Well, we noticed earlier, when we were just looking at all those parabolas side by side on the same graph, we noticed earlier that all parabolas are similar to each other. It's just a matter of being shifted, stretched, or flipped compared to that fundamental f of x equals x squared, that fundamental square function. Now, shifted, stretched, flipped, that sounds exactly like transformations. Remember when we learned about transformations when we were first talking about functions? So we go back to our lesson on transformations and we refresh ourselves. So let's pretend that we just went back and we grabbed how the transformations for vertical shifts, horizontal shifts, stretches, and vertical flips work. And any of this stuff is really confusing in this lesson, go back and watch that there, and it'll give you a refresher and go, oh, that makes sense how these things are all coming to being. It all gets fully explained in that lesson, so if you didn't watch it before, might be a good thing to check out now. So we go back, we grab that information. Always useful to think in terms of, I learned this before, that would be useful now. Then you just go back, you look it up in a book, you find it on the internet, you watch a lesson like this at educator.com, you relearn what you need for what you're doing right now. Reviewing our work in transformations, we get vertical shift is f of x plus k. So we have f of x is just x squared, because that's our basic fundamental square function. And we add k, and that just shifts it up and down by k. Horizontal shift is f of x minus h, so f of quantity x minus h. So that's going to be x minus h plugging into that square, so it will be x minus h, and then that whole thing gets squared. And that's going to shift it by h. So positive h will wind up going to the right, negative h will wind up going to the left. Stretch, if we want to stretch it, we multiply by a times f of x. So as a gets larger and larger, it'll be more stretched vertically because it's amping it up. And as a gets smaller and smaller, closer and closer to 0, it's going to squish it down because it is taking it and making any given value output smaller. And then finally, vertical flip. Vertical flip is just based on the sign, so it's going to be a negative in front will cause us to go from being up to being down, because everything will get flipped to its negative output. Now, one quick note, we're now using a slightly different form to shift horizontally. So previously, we were using f of x plus k, but now we're using f of x minus h, right? F of x minus h is what we're using right now, quantity x minus h and quantity squared. And that's going to help us with parabolas, and we'll see why in just a moment. It's going to just make it a little bit easier for us to write out a formula for the vertex. Now, for x plus k, positive k shifted to the left. But now when we're using x minus h, positive h will shift to the right. Now, why is that? Remember, so if for x plus k, when we plugged in a negative 1, it caused us to shift to the right, then if we plug in a positive h, that's just going to be the same thing as a negative k, right? Positive h is equivalent to a negative k, so a positive h goes right, a negative k goes right. A negative h goes left, a positive k goes left. For now, we can just switch our thinking entirely to this x minus h squared form, because that's what we'll be working with right now, but it's useful to see what the connection is between when we first introduced the idea of transformations in our previous lesson to what we're working with now. All right. We can combine all this together into a new form for quadratic polynomials. A times x minus h squared plus k. This shows all the transformations a parabola can have. Our vertical shift, that is the plus k over here. The horizontal shift, that's the minus h portion inside of the squared. The stretch or squeeze on it is the a right there. And then the vertical flip is also shown by the a just based on the sign of the a. If the a is positive, then we're pointed up. If the a is negative, then we're pointed down. So all the information about a parabola can be put into just these three values, k, h, and a. And this also makes sense because in our normal form, ax squared plus bx plus c, all the information about a parabola can be put in 1, 2, 3, A, B, C. All the information you need to make up a quadratic can be put into A, B, and C. So clearly it just takes 3 pieces of information to say exactly what your parabola is. So it shouldn't be too surprising that there's 1, 2, 3 pieces of information if we've swapped things around into a different order of looking at it. We can convert any quadratic we have into this form, this a times x minus h squared plus k form. For example, all the various parabolas we saw earlier, f of x is the one in red, g of x is the one in blue, h of x is the one in green, and j of x is the one in purple that I confusingly am using yellow to highlight. Sorry about that. So if we look at this, 1 times x minus 0 squared plus 0. So this means a shift horizontal of 0, a shift vertical of 0, and it is a non-stretched, a normal looking thing. And that's exactly what we've got right here with our red parabola. Seems pretty reasonable. Blue one, x minus 2, means that we've shifted to the right by 2, and we've shifted down by 3. And that's exactly what's happened here. We're at 2 in terms of height, 2 in terms of horizontal location, and 3 in terms of height. And then 4, the 4 here means that we've stretched up, which seems to make sense because it seems to be pulled up more than when we compare it to the green one. Similarly, we've got similar things with green. It's been moved. The negative 1/5 causes it to flip out and sort of stretch out. It's been squished out, so it's not quite as, long. And then, once again, our confusing yellow is purple. Negative 11, it's been flipped down, and it's even more stretched out than the blue one is. It's even more stretched out because it has a larger value, 11 versus 4. The negative just causes it to flip. So we see how this stuff connects. How do we convert from our general form, ax squared plus bx plus c, into this new alternate form? We're used to getting things in the form ax squared plus bx plus c. We're used to working with things in the form ax squared plus bx plus c. So we might want to be able to convert from ax squared plus bx plus c into this new form that seems to give us all this information. It's very easy to graph with this new form because we just set a vertex and then we know how much to sort of squish it or stretch it. Now, how do we do this? We do it through completing the square. So if you don't quite remember how we did completing the square, if you didn't watch the previous lesson and you're confused by what's about to happen, just go check out the previous lesson. It'll get explained pretty clearly as we work through that one. So assuming you understand completing the square, let's see it get used here. We've got ax squared plus bx plus c right here. And so what we do is we take the c, and we just sort of move it off to the side, so we don't have to work with it right now. And then we put parentheses around this, and we pull the a out of those parentheses. So since we divide this part by a, since we divide the ax squared by a to pull it out right here, then we also have to divide it from the b as well, so we get b over a. So we've got a times quantity x squared plus b over a times x, and quantity plus c. So if you multiply that out, you'll see, yeah, you've got the exact same thing that you just started with. Next step, remember, when you're completing the square, you want to take this thing right here, and then you want to divide that by 2, square it, and then plug it right back in. So if we do work through this, we get b over a over 2 would become b over 2a. Then we'd square that, and we'd get b squared over 4a squared. So that's what we're plugging in right here, b squared over 4a squared. But since we're putting something in somewhere, we've got to keep the scales balanced, right? If we put one thing into some place, we can't just have nothing else, counteract that. For example, if I had 5, and I wanted to put in a 3, just for some reason I felt like putting in a 3, 5 is totally different than 5 plus 3. So you have to put in something else to counteract that. What will counteract plus 3? Minus 3 will counteract that. Now notice, though, we've got this a standing in front. So if we put b squared over 4a squared right here, this a is going to multiply it. So it's effectively like we put in more than that, right? So going back to 5 plus 3, if we had a 2 standing out front and we wanted to have this be just the same thing as 2 times 5, we wanted this to be the same as this, then 2 times quantity 5 plus 3, well, this would be the same thing as a 6 inside of it, so we'd have to put a minus 6 on the outside, 2 times 3. We're having this thing on the outside has to be dealt with on what we just added in. Otherwise, we're not going to have equal scales, right? We've got this thing on the outside, this extra weight sort of modifying things, this a on the outside of our quantity. And so if we don't deal with that, when we figure out how much to put on the outside part, minus 6 or minus 3, it's going to wind up not being equal on the two sides anymore. So if that's the case, then we've got minus b squared over 4a, because if we think about it, we've got the yellow a, right? Yellow a, just because yellow's a little bit hard to read. So a times this thing right here, b squared over 4a squared. So that winds up being the a here and the a squared. The a squared cancels to just a, and that cancels that a right there. So we've got b squared over 4a, and so that right there is what we're going to need to subtract by. We'll subtract by that, and we'll wind up having it still be equal. And if you work that out, if you multiply that a out into that entire quantity and check it out, you'll see that we haven't changed at all from ax squared plus bx plus c. It's still equivalent. So at this point, we can now collapse this thing right here into a squared form, x plus b over 2a squared. Let's check and see that that actually makes sense still. X plus b over 2a squared. So we get x squared, x times b over 2a, plus b over 2a times x, so that becomes b over a x, because they get added together twice, plus b squared over 4a squared. So sure enough, that checks out. That's the same thing. Minus b squared over 4a plus c. We just want to put that over a common denominator. So if we have c, that's going to be the same thing as 4ac all over 4a. So now they're over a common denominator. So this plus c here becomes the 4ac right there. So we've got negative b squared plus 4ac over a. And now we're back in that original alternate form. Or sorry, not that original alternate form. We've gone from our original normal form of ax squared plus bx plus c into our new alternate form. We'll see how it parallels in just a moment. In our new form, it's really easy to find the vertex. We've got a times x minus h squared plus k. So from our information about transformations, we see that the vertex has been shifted horizontally by h, horizontal shift of h, and then vertically by k. So in this form, our vertex is at h, comma, k. Simple as that. What about ax squared plus bx plus c if we started in that way? Well, we just figured out that ax squared plus bx plus c is just the same thing as this right here. Now that's kind of a big thing, but we can see how this parallels right here. So we've got negative h here, we've got plus b over 2a here. So as h, it must be the case that we've got negative b over 2a, because otherwise we wouldn't be able to deal with that plus sign right there. Then we've also got the plus negative b squared plus 4ac all over 4a, and that's the exact same thing as our k. Since they're both plus signs here, they wind up staying the same value. We've got negative b squared plus 4ac over 4a, so that gives us our vertex. Now, I think it's pretty difficult to remember negative b squared plus 4ac all over 4a, since it's also different than our quadratic formula, but it's a lot like it, so we might get the two confused. So what I would recommend is just remember that the vertex, the horizontal location of the vertex, occurs at negative b over 2a. And then, if you want to figure out what the vertical location is, just plug it in to your function, right? You have to have your function to know what your polynomial is. So you've got negative b over 2a will tell you what the horizontal location of the vertex is, and then you just plug that right into your function, and that will, after you work it through, spit out what the vertical location is. Seems pretty easy to me, and much easier, I think, than trying to memorize this complicated formula. So I would just remember that vertexes occur horizontally at negative b over 2a. Great. By knowing the vertex of a parabola, we also know the minimum or maximum that the quadratic attains. So if a is positive, it cups up, right? It goes up. So if it cups up, then we're going to have a minimum at the bottom. So if a is positive, it cups up, right? Then we will have a minimum at x equals negative b over 2a, because that's where the vertex is. And clearly that's going to be the most extreme point. Vertex is going to be the extreme point of our parabola, whether it's high or low, depending. Then if we have a is negative, then that means we are cupping down, right? It points down, so if we're cupping down, then it must be the high point is going to be the vertex. So maximum, if we have an a is negative, because we're cupping down, so it'll be x equals negative b over 2a. Now you might have a little difficulty remembering a is positive means minimum. That seems a little bit counterintuitive probably. A is negative means maximum. What I would recommend is just think a is positive means that it's going to have to cup up. O, the vertex has to come at the bottom. A is negative means it has to cup down. O, the vertex is going to come at the maximum. Remember in terms of that, just honestly making a picture in front of your face, being able to just use your hands, gesticulate in the air in front of yourself and see what you're making in the air, that makes it very easy to be able to remember this stuff. Just trying to memorize it as cold, dry facts, not as easy as just being able to go, oh, I see it, that makes sense. You're remembering the primary concepts, and from working from there, it's much easier to work things out. All right. Also, if we know the vertex, it's pretty easy to find the axis of symmetry, right? The axis of symmetry runs through the vertex. Since it has to go through the vertex, and the vertex is at a horizontal location of h, then it's just going to wind up being a vertical line, x equals h. So for example, if we had f of x equals x minus 1 squared minus 1.5, then we'd know that would give us a vertex of x minus h plus k. So it would give us a vertex of minus 1 becomes h is just 1, and then k, since it's plus k, it means that k must be negative 1.5. We don't really care about the negative 1.5 since we're looking for a vertical line that's just x equals h. So we take that x equals h and we make x equals 1. So we get an axis of symmetry that runs right through the parabola at a horizontal location of 1, and sure enough, that splits it right down the middle. Nice axis of symmetry. And here's an incredibly minor note on grammar. This is really minor, but a lot of people are confused by this grammar point, so I just want you to have this clear so you don't accidentally, say the wrong thing and it winds up being embarrassing. You might as well know what it is. Singular, the singular form, if you want to just talk about one, is vertex. Singular form, if you want to just talk about one, is axis. On the other hand, if you want to talk about multiple of a vertex, that's going to be vertices. So multiple vertex, multiple vertices is what it becomes. Vertex is kind of hard to say, so that's why it transforms into vertices. Axis becomes axes. So axis, axises, once again, sounds a little bit awkward, so we make axis becomes axes. So it's not just one vertex, but many vertices. The Earth has one axis, but the plane has two axes. So really, really minor thing, but you might as well know it because you occasionally have to say this stuff out loud. All right, we're ready for our first example. So if we've got this polynomial, f of x equals negative 3x squared minus 24x minus 55, and we want to put this in the form a times x minus h squared plus k, then we'll identify what a, h, and k are. So how do we wind up doing this? We have to complete the square. So we've got to complete the square, and we're going to complete the square on our polynomial negative 3x squared minus 24x minus 55. All right, so once again, if you don't quite remember how to complete the square, you can also get a chance to see more completing the square in the previous lesson, but you also might be able to just pick it up right here. So first thing we have to do, we have to separate out that minus 55 so we can see things a little more easily. So we aren't actually going to do anything to it. We're just going to shift it, literally shift it to the side just so we can see things and keep our head clear of the minus 55. Still part of the expression, we're just moving it over right now. Now we want to pull out the negative 3 to clear things out. So if we're pulling out negative 3 on the left, we have to pull out negative 3. If we're pulling negative 3 out of negative 3x squared, we also have to pull out of negative 24x. So if we're going to do that, if we're pulling out negative 3 out front, negative 3 dividing into negative 3x squared, so negative 3x squared divided by negative 3 becomes just positive x squared. Great. And then negative 24x divided by negative 3 becomes plus 8x minus 55 still. Now, we might be a little bit unsure of this. Doing the distribution property in reverse, might be a little bit worrisome. We're not used to doing that yet. So we might want to check this. Negative 3 times x squared plus 8x, negative 3x squared minus 24x, great, that checks out just like what we originally had. So negative 3 times quantity x squared plus 8x minus 55 is the exact same thing as what we started with right here. So checking like this, probably fine to just do it in your head. You could do negative 3 times that quantity in your head and go, yes, this makes sense. But if it's an exam, if you're something like that, you definitely want to check under those situations. Make sure that, if it's something really important, you're really checking and thinking about your work, because it's really easy to make mistakes, especially if it's new to you. All right, so negative 3 times quantity x squared plus 8x. So how do we get this to collapse into a square? How do we get this to actually pull into a square? Well, if you remember, when you're talking about completing the squares, we want to take this number, and we want to add in 8 divided by 2 and then squared. So 8 over 2 squared is 4 squared, which is equal to 16. So we want to add 16 inside. So we've got negative 3 times quantity x squared plus 8x plus 16. So we're adding 16 in. But now, remember, if we're putting something into the expression, we have to make sure that, we keep those scales balanced. If we put 16 in, we've got to take away however much we just put in. Now, we didn't just put 16 in. There's also this -3 up front. So we put 16 into the quantity, but that gets multiplied by -3 as well. So what did we put in total into the expression? We put -3 times 16 in total into this expression. -3 times 16, 3 times 10, 30, 3 times 6, 18. So it's -48 in total. So if we put -48 into the expression, we need to take -48 out of the expression. So what's the opposite to -48? +48. So if we put -48 in and we put in +48, at the same time, it's going to be as if we had done nothing. So we've got that positive 16 inside of the quantity, but because of that -3 out front, it's as if we'd put in a -48, so we put in a +48 outside of the parentheses, and it's as if we'd had no effect at all. So it's still equivalent to what we started off with. +48 minus 55. At this point, we just finish things up, collapse the stuff. X squared plus 8x plus 16 becomes x plus 4 squared. We know that because it's going to wind up being 8 over 2, which is 4. Let's check it real quick. X plus 4 squared, x times 4 plus 4 times x, 8x, 4 times 4, 16. Great, checks out. And then plus 48 minus 55. So 48 minus 55 becomes plus -7. Great. So at this point, we're ready to identify. We've got A is -3, because that guy is in front of our multiplication. Then B, whoops, sorry, not B, but H. H is equal to -4, because it's the guy right here, but notice it's -h, and what we've got is +4. So since we've got +4, it has to be H equals -4, otherwise we're breaking from that form. And then finally, K is equal to -7. Great, and we've got everything we need to be able to put it in that form. All right, next example. Give a function for the parabola graph below. So we've got this great new form, and look at that. It looks to me mighty like we've got the vertex right here. It's pretty clearly the lowest point on that parabola, so it must be the vertex if it's the absolute lowest point on a parabola that's pointing up. So f of x equals a times x minus h squared plus k. Great. So what is our h comma k? Well, h comma k is going to come out of this. So h comma k is what our vertex is, which is 2, 1. So h equals 2, k equals 1. We plug that information in, and we're going to get that f of x is now equal to a times x minus 2 squared plus 1. All right, so we're close, but we still don't know what a is. But hey, look over here. We've got this other point over here with additional information. So we know that when we plug in -1, we get out 4, right? F of -1 equals 4. So now, if f of -1 equals 4, then we can say that 4 equals a times -1 minus 2 squared plus 1. 4 equals a times -3 squared plus 1. 4 equals a times 9 plus 1. We subtract the 1 from both sides. We get 3 equals a times 9. We divide out the 9, and we get 1 over 3. 3/9 becomes 1/3 equals a. So finally, our function is f of x equals 1/3 times x minus 2 squared plus 1. Great. And if the problem had asked us to put it in that general form, ax squared plus bx plus c that we're used to, at this point you could also just expand 1/3 times x minus 2 squared plus 1, and you'd be able to expand it and work through it, and you'd also be able to get into that form, ax squared plus bx plus c. Remember, you can just switch from one to the other. To switch from this form, this new form, into our old general form, you just expand. If you want to go from the old general form, you complete the square like we just did in the previous example. All right. Third example, f of x equals 6x squared minus 18x plus 5. Does f have a global minimum or a global maximum? And then, which one and at what point? So, if f of x equals 6x squared, then notice ax squared plus bx plus c, they wind up being the same in f of x, a times x minus h squared plus k. So a equals 6. So if a equals 6, then a is positive. So if A is positive, we've got cups up. So if it cups up, then it's going to have a minimum. So what it has is it has a global minimum on it. Now, where is it going to happen? Vertex horizontally is x equals negative b over 2a. So what's our b? Our b is negative 18, remember, because it's ax squared plus bx. So if it's negative 18, then b is negative 18. So we've got negative, what's b? Negative 18 over 2 times, what was our a? 6. We simplify this out, so we get positive 18 when those negatives cancel over 12 equals 3 halves. So our x location is at 3 halves. And now what's our y going to be at? Well, we can figure that out by f of plug in 3 halves equals 6 times 3 halves squared minus 18 times 3 halves plus 5. So we work through that. 6 times 9 over 4, we square both the top and the bottom, minus 18 times 3 halves. Well, we can knock that out, and this becomes a 9. So we've got 9 times 3, or minus 27, plus 5, equals 6 times 9 over 4, well, this is 2 times 2. 6 is 3 times 2, so we knock out the 2's. And we've got 3 times 9 up top, 27 over 2, minus what's 27 plus 5? That becomes 22. So we can put those over, minus 22 over a common denominator with 27 over 2. We get 27 over 2 minus 44 over 2. 27 minus 44 over 2. 27 minus 44, and we get negative 17 over 2. So that's our y location. So that means the point where we have our minimum is point 3 halves, comma, negative 17 over 2. And there is the point of our global minimum. Great. All right, final one. This one's a doozy of a word problem, but it's a really great problem. Norman window has the shape of a semicircle on top of a rectangle. If the perimeter of the window is 6 meters in total, what height h and width w will give a window with maximum area? So at this point, how the heck do we do this, right? So first thing we want to do, we want to understand what's going on. So this seems to make sense, right? We've got a semicircle, right? That's our semicircle right here. What's a semicircle? A semicircle is just half of a circle. And yeah, that looks like half of a circle on top of a rectangle. So it's on top of a rectangle, and we've got our rectangle right here. So that seems to make sense, right? We've got a semicircle on top of a rectangle box. Okay, that idea makes sense. The perimeter of the window is 6 meters. Now, we might have forgotten what perimeter is, but perimeter is just all the outside edge put together. So nice, hard to see yellow. So we go outside perimeter, 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 perimeter. So it's going to be all of the outside of that box, but it is not going to go across now. It's going to also have to be outside perimeter of the top part of the window, right? We've got that dashed line there to indicate that's where we split into the semicircle, but there's no actual material there. It's just the perimeter is the very outside part. So the perimeter will be the top part of that semicircle and then 3 sides of our box. The 4th side doesn't actually exist. It's just connected into the semicircle. All right, so that makes sense. We know that is 6 meters. And then we want to ask what height and width will give a window with maximum area. So if we're looking for area, we're probably going to need to use area, right? So A equals area. We'll define that idea. If we also know information about the perimeter, then we'll say P equals perimeter. Okay, so let's work these things out. So if area is equal to the area of this part plus the area of our box. So it's the area of our semicircle plus the area of our box. So area of our semicircle, well, what's the area of a circle? So circle, area for a circle is equal to pi r squared. So a semicircle, if it's a half circle, that's going to be area equals 1/2 pi r squared, because it's half of the circle, right? So we've got 1/2 pi r squared. Well, hey, we don't have an r yet, so we better introduce an r. So we'll say, here's the middle. So r is from the middle of our circle out like that. So area equals pi r squared divided by 2, because remember, it's a semicircle, so it's half of it, plus what's the area of our box? That's height times width. so height times width. Now, we don't really want to have r, right? The fewer variables, the better if we're going to try to solve this. So how does r connect to the rest of it? Well, r, hey, look, that's connected to our w because it's just half of that side, So r equals w over 2. So we can change this formula into area equals pi r squared is w over 2 squared over 2 plus height times width. Now we've managed to get rid of the radius there, so let's simplify that out a bit more. Area equals pi squared, the w over 2, that begets w squared over 4 over 2 plus hw. So we've got this whole thing divided by 2, so area equals pi w squared. And we're dividing, so with the 4 and the 2, since they're both dividing on pi, dividing on that stuff, they're going to combine into divide by 8 plus hw. Great. So we've got area equals pi w squared plus hw. All right. What about perimeter? What can we say about perimeter? Well, the perimeter is going to be equal to, well, there's an h here, there's a w here. What's here? Just another h. And then what is this portion here? So right off the bat, we see we've got two h's plus a w plus something else. So circumference for a circle, right? If we want the perimeter of a circle, that's circumference. So circle circumference is equal to 2 pi r, 2 pi r. But if it's a semicircle, then it's half of a circle, so it's going to be 2 pi r divided by 2. So perimeter for a circle will be, perimeter for a semicircle will be 1/2 times 2 pi r, which is just going to be pi times r. So we've got 2h plus w plus the amount of perimeter that our semicircle puts in is pi r. Now once again, we don't really want to have extra variables floating around, so we want to get rid of that. So perimeter equals 2h plus w plus pi times w over 2. Great. So at this point, we see that we've got h and w, we've got area. So if we could turn this into, we've got area is unknown. We don't really know what the maximum area is or what area we're dealing with. Really, it's a function that's going to give area when we plug in h and w, so it's not even something that has a fixed value necessarily. What about perimeter, though? Perimeter, that is something we do know. Remember, perimeter is 6 meters. So we can plug in 6 equals 2h plus w plus pi w over 2. Now it seems like we've got more w's than we've got h's in both area and our area and perimeter stuff. So let's try to get rid of area. So we'll figure out what we'll figure out what h is in terms of w, so we can substitute out the h and switch it in for stuff about w. So we'll move everything over. We've got 6 minus w minus pi w over 2 equals 2h. We divide by 2 on both sides. We get 3 minus w2 minus pi w over 4 equals h. And now let's just pull those things together so it'll be easier to plug in later into our 1 over here, because we want to swap out the h here for it. So 3 minus 2w over 4 plus pi w. Now that part might be a little confusing, but notice that this has minus and this has minus, so when we combine them together, they're just one minus because they're actually working together before they do their subtraction, equals h. And we can even pull out the w onto the outside, so we get 3 minus 2 plus pi over 4 times w equals h. Great. So now we've got an expression about area, and we've got an expression about h and w. So at this point, we can plug in what we know about h, and we can plug it in for the h in the hw in our area, and we'll have area equals just stuff involving w. And since it's just stuff involving w, we'll have just one variable. Maybe we can figure things out. Maybe it looks like something. Maybe it looks like a quadratic, since after all, this was all about how quadratics work. So student logic seems pretty likely it's going to wind up looking like a quadratic, and we can apply the knowledge that we just learned. So maximum area at what h and w? We've got area equals pi w squared over 8 plus wh, and h equals 3 minus 2 plus pi over 4 times w. Okay, great. So at this point, we take h here, we plug it in over here. So we've got area equals pi w squared over 8, that's still the same thing, plus w times h, so w times, what's h? 3 minus 2 plus pi over 4 times w. We expand that out, and our area is equal to pi w squared over 8 plus w times 3 minus 2 plus pi over 4w. So we get 3w minus, and let's keep it as 2 plus pi over 4, and it just combines with that other w. We've got w squared. Hey, so now we've got a w squared here and a w squared here, so let's make them talk to each other. So we get pi w squared over 8. So let's actually pull that down. So we'll make it as pi over 8 w squared minus 2 plus pi over 4 w squared plus 3w. So now we've got pi over 8, and we can bring this stuff to bear, so it'll be minus 2 plus pi, but it used to be a 4, so it's going to be, to become an 8, we're going to multiply by 2 here to keep it the same. So 2 times 2 plus pi becomes 4 plus 2 pi. So we've got pi minus 4 plus 2 pi, 8 w squared plus 3w. We simplify this out. Pi minus 4, so the negative 4 will come through, and minus 2 pi will become minus pi over 8 w squared plus 3w. Hey, look, if area equals this, then this right here, this whole thing, is a quadratic. So if it's a quadratic, then we can use the stuff that we know about where vertices show up. Where do vertices show up on the parabola? Now, we're looking for the maximum area, so we better hope that our parabola points down so it does have a maximum at its vertex. Sure enough, we've got a negative here and a negative here, and since that's on the w squared, that means we could pull out the negative, and our first a is going to be negative quantity 4 plus pi over 8. So that whole thing winds up being a negative number. So sure enough, it is going to have a vertex at the top, so it will have a maximum area out of this. It is cupping down. So at this point, we figure it out. So remember, vertex is at our horizontal location. So in this case, horizontal would be just our w. Vertex is going to be at w equals negative b over 2a. So what is that? So it's going to be w equals, what is our b? That's going to be 3. So we've got negative 3 over, what is a? A is this whole thing. So negative 4 minus pi over 8. So this is a little bit confusing, but we've got a fraction over a fraction. So if it's like this, we can multiply the top and the bottom by 8. So 8 on top, 8 on the bottom, we'll get negative 24. And the 8's down here will just cancel out. So we'll get negative 24 minus 4 minus pi. We see that there's negatives everywhere, so we can cancel out all of our negatives, multiply the top and the bottom by negative 1. We get positive 24 over 4 plus pi. So the maximum is going to happen at 24 over 4 plus pi. There is our, one thing, just realized, made one tiny mistake. It's 2a, right? So we've got a 2 here, so it's still a 2 up front, so it's not 4 plus pi. Always important to think about what you're doing. 24 over 2 times 4 plus pi. So that cancels to be 12 over 4 plus pi. Now, that was clearly a very long, very difficult problem, but we see it's actually really similar to the previous example that we just did. All we're looking for is where's the vertex. The only thing that this is it's couched inside of a word problem, so we just have to be carefully thinking, how do we build equations? Once we've got our equations built, how do we put them together? How do we get this to look like something where I can apply what I just learned in this lesson, how I can apply this stuff about quadratic properties. So we find out that the maximum occurs when w is equal to 12 over 4 plus pi. Now they asked, what h and w? So since we have to figure that out, we know h is equal to 3 minus 2 plus pi over 4 times w. So h is going to be at its maximum as well, since it's the h and w. 3 minus 2 plus pi over 4 times 12 over 4 plus pi as our w. So we notice that 4 can knock out the 12, and we'll get 3 up top. So we get h is equal to 3 minus 2 plus pi, so 3 times 2 plus pi over 4 plus pi. We want to put them over common denominators so we can get the two pieces talking to each other. So we've got 3 times 4 plus pi over 4 plus pi. And then it's going to be minus 3 times 2 plus pi, so minus 6 minus 3 pi. So we've got 12 plus 3 pi minus 6 minus 3 pi all over 4 plus pi. So finally, our h is going to be the minus 3 pi's cancel each other out. 12 minus 6, we get 6 over 4 plus pi. And that's our value for what our maximum h will be with our maximum width. So the maximum area will occur when our width is 12 over 4 plus pi and our h is 6 over 4 plus pi. They'll both be in units of meters because meters is what we started with for our perimeter. All right, hope you've got a sense of how quadratics work, what their shape is, and this idea of the vertex, and that being where maximum and minimum are located. And remember, you just have to remember that the horizontal location for maximum or minimum, the horizontal location for vertex, is going to occur at negative b over 2a when we've got it in that standard form of ax squared plus bx plus c. As long as you remember negative b over 2a, you can just plug it in anytime that you need to find what the vertical location going along for that vertex is. All right, we'll see you at educator.com later. Bye.